Hi there. Can you hear me? Great. So it's 3 o'clock. I'll get started. I'm going to be talking to you about robotics and why embedded Linux is where we're headed, / where we've already gone, and where we're going to be headed next. So, give you a little bit of my background first. Let you know who I am, where I'm coming from. I've been doing robotics for a while. How many of you are familiar with the DARPA Grand Challenges? Okay, great. I've been involved in all 3 of those, and I'll go into more detail on those later. I've got some videos that are fun. After working on autonomous cars in the Grand Challenges, I moved on to Willow Garage, where I worked on the PR2, and I've been a core developer of ROS, the robot operating system, since very early on. And there I worked on both the PR2, and I'm also one of the co-creators of the TurtleBot, which is a small educational research platform, which lets you get access to and learn about ROS before you go and raise funding for a larger robot. Okay, sorry, I gotta get the clicker working. Where I'm coming from, I work at the Open Source Robotics Foundation. We're a 501c3. You can see our mission statement is up there. That is in our incorporation documents. We're required to work on projects that promote open source robotics, education, outreach, and research. There are 16 of my colleagues there. We're based in Mountain View, California. So quick jaunt north. And I want to give you a sense of Sorry. No more clicker. It's not working. So robots are actually quite young. Just to give you a sense of perspective, the term robot was coined in 1920. And the term robotics itself, robot was coined in 1920. The term robotics was only coined in 1941 by Isaac Asimov. And from the meaning of robot is forced labor based on Czech derivation. So, not quite 1941, but more recent than that is 1961. This is one of the first robots that actually you would probably recognize as a robot. So this is a news clip from 1961 where they're actually showing off this robot on a variety show type situation. It's the Unimate, and they advertise that this is the thing that's going to replace all workers and can do everything with precision. It doesn't get tired, but it also, you'll note, it's very precise. But it doesn't have any feedback. It does exactly the same thing every time. But it's surprisingly similar to all of industrial automation since then. So looking forward, there's a general theme of why we're going toward embedded Linux is cost reduction. So another early robot is Shaky. It was developed at SRI. If I jump to 17 minutes here, you can see this is a robot walking around in a very realistic world where everything is perfectly prismatic. It's either white or red, and you can then navigate through it. For reference, this is using an SDS 940 before Xerox bought it when it became an XDS. You can get more information from SRI's website there. But this robot was state-of-the-art, brand new computers back in the day. It can navigate around. It can keep track of the obstacles that it knows exactly the size and shape of. And it's a great demonstration of all those things that we want robots to do. But it really could only do it in a contrived environment using I have no idea what this cost to build, but you can see it was like 6-year project to actually build it, with probably a lot of researchers doing it, and the cost of the robot was similar to the researchers' salaries at the time. And if you look at the picture on the left, you can actually see some of the components called out. It's basically a wheeled base, batteries down the bottom, computer, and then a camera up top. And the difference is that that used to cost a fortune, and now people build a copy of this at home with off-the-shelf parts. I was searching for the other video, and I ran into this one, which is embedded on YouTube, and it's your standard hobbyist robot. It has the cat in the background of half the shots. And it's just off-the-shelf parts, pulling them all together, which shows you how much change there has been in the last 30 years, and we're continuing that trend, which is pushing smaller and smaller. So looking more at the personal robotics space, in fiction we have some very, very capable robots. You've got Terminator in the Terminator series. This robot can see better than you, it can run faster than you, it's stronger than you, it's smarter than you. And likewise, we have a little bit older Rosie the robot on the Jetsons. She's the robot that will come into your home and take care of anything that you don't want to do, so that you just sit around and do what you enjoy doing and don't have to worry about any of the chores. These are great visions. They've been around for a while, but it turns out we're not really there at the moment. In reality, we have humanoid robots that can barely stand up, and we have robots that can fold towels. This is results of research from a DARPA program that ran last spring on the left, and on the right is a towel folding robot. And what you can't see in the towel folding robot is this is a speed time lapse with 50x. So it took something like 2.5 hours per towel that it folded. They got it faster over time, but it's not a trivial amount of work to do. And it's kind of horrible to watch all these, but they are fun to watch. That's a good example of where it was just a software configuration. They had 2 different controllers for the leg, one for walking and one for driving. And they forgot to turn off the driving controller when they were starting to transition to walk. So as they stepped out of the vehicle, there were 2 controllers fighting for control of the leg. And that's why you can see it jiggling, because one's saying step down and one's saying press on the gas. So we're making progress on the research. But in reality, for personal robots, the only one that's really out there is the Roomba. It's been around for 10 years, and the big difference with the Roomba is that it's running on a microcontroller. It's not running a microprocessor. It doesn't have much logic. If it wants to find its way home and it's not in front of its beacon, it has the very scientific approach of doing a random walk until it sees its beacon, and then it can home on the beacon. The other one is up here is the PackBot. This is one of the military ones for explosive disposal. And it does not have much intelligence inside. It's basically the human remotely operates it to do every single task, every single little motion. They're slowly adding functionality to help it be able to do more. But in reality, it's just remote control. That's why the people operating it that are the best at operating are the guys that have played video games the most. That's actually a valuable skill now in the military, because if you've played a video game, you can control one of these robots better. But looking at cost, if you want to go to volume in robotics, you need to have the unit cost way down. which is another thing that is super valuable with embedded Linux as we start to look at what options are available there. So I want to give you another perspective. Autonomous cars is something I've been involved with personally for a while. Again, starting off with the reference point of what you can see in fiction. This is a GIF of iRobot, the autonomous driving car, while Will Smith is browsing the magazine before he has to take over control and control the car and go save the world. We're not there yet. Bit of perspective, I told you I was working on autonomous cars in 2004. This is our vehicle. If you look closely, you can see through the plexiglass on the side, we have about 8 desktop computers bungee cord down on foam pads inside of the back there on shelves. We were one of the top most competitive teams. We were able to make it 3 miles out of the 127-mile course. And we ended up failing because we drove through one barbed wire fence going downhill. We tried to get back through. We dodged through a bunch of scrub brush, and then we tried to go back uphill through the barbed wire fence. But we were too conservative on our throttle limits, and we couldn't knock the fence over and then drive over it. Carnegie Mellon made it the farthest with 7 miles, and they went out because there was a gate, and typically you drive through the gate. They drove through the fence post, bent their steering shaft, and high-centered themselves in the next mile. A little bit more fun. DARPA considered that a good response. They did not as much as they wanted, but they continued to sponsor another challenge, and I was involved in this one again. We had a new vehicle, and we have the distinction of being the only team that is able to, has documentation of how their vehicle ended the race. As you can see, we're coming back. We're going to go past the press area on the right, and then you'll see a bunch more people in the spectator area. There was like 300 yards of spectator area. So we chose the right area to step out of the race. You can see the robot getting, it's stopped under some power lines. It lost its GPS, but it says, well, I can't reacquire GPS, and kept going. There was a bug in the reinitialization code which made it thought it was driving straight down the road, but it was actually off by a couple degrees. And you'll see that this has a poor effect. It's a fun video. I like showing it. It shows you quite where we were before, and this is only just over 10 years ago now, which is kind of hard to believe. There were 5 other teams that completed this race. This is the view from the other side. So, a lot of fun projects. We were running inside of this was several rack mount computers, and you can see on the back we actually had a generator attached to the vehicle. We had a large alternator on this, but it was not enough to power the computers. We actually needed a generator bolted to the back of the car to run AC power inside to keep the computers running for several hours. The third time around, DARPA decided they'd figured out how to do it outside in the desert, and now they wanted to bring it into an urban environment. This is the third car I worked on, Little Ben, and in this challenge, you no longer were out in the desert and alone. You actually had to deal with 4-way stops, precedences for when you pull up to the stop line, which other cars were there first, merging and multi-lane traffic. In the competition, there were something like 10 vehicles on the course at once, and it was a small, several block radius type environment. And they also hired race car drivers and put them in as cars to pretend to be traffic. So you actually had to deal with traffic, and they'd set you up on a 4-way stop, and they'd have the human drivers make sure to sequence in, and you got scored whether or not you followed the appropriate California state driving laws. You can see on the back we were actually using Mac Minis at the time. The computers are getting smaller, less power. We were able to run the whole car, all the computation off of the hybrid power in the Prius, which was really great. You found a lot of teams picked hybrid cars because they had a large battery pack that could support the large AC load. And of course today, You know that Google's out there driving lots of miles. There's now, I think, 7 companies which have authorization to have drivers on the California roads to testing. If you go to the California DMV website, you can click to fill in the form to apply for yourself as well. So we made huge progress in that in just the last 10 or so years. So as I mentioned briefly about the power requirements, this is Atlas. You saw several clips of him falling over. He's a very impressive robot. He can do a lot of things. But I want to point out the big looping cable that's behind him. That's his power cord. This robot takes something like 5 kilowatts to make him walk. And when he's standing and sort of just balancing, it's not quite 5 kilowatts. Estimates run that it's something like 1 to 2 kilowatts, which is not really okay for running on battery packs. They actually did. Those videos I showed you earlier showed the robots with battery packs. But those battery packs were so dangerous that the manufacturer would not ship them to any of the teams that had Atlases at their facilities like this one. They would only provide the battery pack to them at the competition. So prior to the competition, these robots had never seen the battery pack. They actually have a battery pack simulator where that cord plugs into, and it pretends to be the battery pack and gives you the voltage that drops off as if it's a battery. But you could not actually test with the battery because that much lithium is a hazard to ship. Similarly, the PR2 is the robot I worked on. It's a humanoid robot. It's got wheeled base, it had humanoid arms, which are great because we can't gravity counterbalance them. So with that, we were able to the whole robot could run with 200 watts of power. But down in the base, you can see we had that's one of the servers being pulled out for maintenance. That server had 2 quad-core i7s in it, and there were 2 servers. So we had 16 i7 cores, and if we loaded up those computers, we could actually pull a kilowatt of power. And if you remember, all of the motors in this robot, this 500-pound robot, were 200 watts when maxed out. So as you can see, power is a major issue for robotics. And I tend to say that if you give a robotics researcher computers, like any amount of cores, any amount of computation, they will use up all of it and ask for more. We gave them 16 cores of i7, and they said, that's not enough. We need more. We gave them gigabit backplane. They're like, we want more. We have to have 2. We have to run them in parallel so they don't collide, so we can fill up the bandwidth more. So now as we're looking, another thing that robots need to deal with these days is more dynamic and complex environments. On the left, you can see a very classic robot. It doesn't deal with any of these things. It is bolted down. It has external power. It has one task. It is custom built for that exact task, and it puts that windshield into that car, and that's all that it does. On the right, you can see, however, is a Baxter robot. And the goal of this is to support light manufacturing and short-run manufacturing. So you actually use the user interface where you grab the arms, push a button, and say, learn this move. And then you can teach it to pack things into a box by just interacting with the robot. And you're not supposed to have to code at all. It does obstacle avoidance. It does. It's designed to be human safe with passively compliant arms so that it does not need to be in a cage. You can see on the left, the robot, it's got its work cell, and if any human goes within basically 20 feet of it, it turns off. It's got sensors to say that, and you will shut down the whole assembly line if you go into that space. Whereas you can see the Baxter is designed to be able to work in reach of humans, and actually they've got demos of it working opposite sides of a conveyor belt as well. But the other thing is that we also need to start dealing with the dynamic environments, both with humans in the area, but also the things coming down the conveyor belt may not be exactly in the right place. What you can't see on the left is that car is fixtured very precisely down to probably something like the millimeter as to where the whole vehicle is so that the arm can hit the right spot. Because just like that arm I showed you at the beginning, it's very good at doing the exact same thing. It is not good at adjusting for whatever needs to be compensated in the area. So another thing, if you look at the left and you look at the right, you've got highly trained operators that are flying a drone. That's probably an older workstation. And now on the right, you have people that are picking up drones and flying them, and they probably paid a couple $100 and they're now flying. And the training was whatever they read when they unwrapped the package and took it out of the box and plugged the battery in and forgot to take off the little covers that are on something. We now have it to the point that robotics needs things that just work out of the box and do all of these system checks, do everything that you need that actually needs to happen before you go flying automatically. And so with this more complex environment, we need to add more intelligence in. With the operator station on the left, it is still basically just remote control. There's probably an autopilot where you say fly this straight line, which is the same thing that pilots actually use on planes. But when you start talking about a drone with an untrained operator, you now actually have to have it do all the system checks, do all the automation and everything to make sure that the system works, because the untrained operator is going to do the wrong thing if they are required to do it. So I've been talking a lot about why we want to use embedded, and now why do we want Linux? Obviously, we're at Embedded Linux Conference. A lot of you know about Linux, so I'm not going to go super deep on this, but just point out some of the things that are valuable to the robotics community. We want the flexibility to customize. We may need to have a special sensor. We may need to have any sort of special hardware, or we need some sort of special mode that we can put it into. Being able to go down under the hood, recompile, fix it, add the functionality, that's super valuable. We both need the flexibility and the freedom to do that. There are a lot of platforms that you just can't do that. But also super valuable to us is the community, the operations for collaboration within the community. There are a lot of robotics researchers around the world. Being able to share these things between everyone and have a common base is also super valuable. Similarly, I mentioned the collaboration, but part of that is also reproducibility. The fact that we can actually have the same image and flash it everywhere, and we can tweak it and send that, and the other person will actually get that same image and be able to reproduce exactly what you've been doing is great. And of course, the lack of restrictions, aka licensing on deployments, is valuable. If you're going to be producing robot products in volume, you don't want to be paying a license per piece of software that you deploy. So I want to give you an example of how the collaboration works using the 2D navigation stack in ROS. We have the same software that we deploy that we developed for the PR2, but we designed it to be robot agnostic. And so you can see that this is a sampling of all the different robots that it runs on and allows them to navigate. It provides localization, path planning, 3D obstacle avoidance, and SLAM just out of the box. So you can actually take this, download it for your robot, parameterize it for your robot, and just launch it, and it'll basically work. And to give you an example of the variety of robots that this works on, here's a montage we did. Ross just turned 8 years old, and we put this together. So you can see, you'll be able to see all the different variety of robots that we're running on. We've got large humanoids, we've got robotic arms, indoors and outdoors, underwater, surface of the water, outdoor desert, logistics, commercial products, on the road, we've got flying, manipulation, and every year the robots get smaller and lighter due to improvements in things like batteries and also the availability of smaller computers. Unfortunately, the bottom right is only simulated moon. It's not real moon. One of the other things that's not evident in these videos is that almost all of our robots are actually robotic systems. They're not just one robot. There's typically infrastructure and other sensors in the environment that you can integrate with and communicate with. So as we branch out to more of those, building up these networked, small, cheap devices becomes more valuable. If you can instrument the room, so the room will just tell the robot where it is, the robot doesn't have to worry about finding out where it is, or at least which room it's in is valuable. So putting this all together, weight means that you take more power to move. More power means you need more batteries. More batteries means you have more weight. And you can get into this cycle that you can't do things if you just are too heavy. Similarly, bigger means that you have more weight, which means you need more power to move, which means you need more batteries. And again, you go into this cycle where you can't actually win. As you get bigger, you just get the problem that you can't drive. Similarly, we need to be reusable so we can share, and customizable so that we can make sure that it's going to work for our application. And lastly, low cost is super, super important because most robotics applications at this point, the Linux computers have been cost prohibitive. As we now are getting the embedded ones, they're starting to become competitive with the microcontrollers, which have been the default. And specifically, why is this applicable to robots? They need real power. I talked about the robots that are out there. They're using kilowatts of power. For every minute of computer runtime, when you put a robot into, like when you park a robot, the motors turn off, but the computer's got to keep running in the background and stay on standby. And you really want robots that are going to be useful. Going back to the real meaning, it's forced labor. We want to be able to have the robots be useful in our world. And to do that, they need to be able to do things like stay online for a whole workday. They need to be able to work and also keep being useful. Also, I haven't mentioned this, but safety is a big problem with robots. As robots are starting to become closer to humans and more interactive with humans, if they're big, they're more dangerous. A small robot is not very dangerous. And if you think about something like your phone, if your phone crashes and turns off, what do? Well, you get frustrated and you move on and keep going. If your robot runs out of battery or crashes and does something wrong and it's stopped in the hallway, you have to walk around it. And if it's big enough, you may not be able to walk around it because it may be the full width of the hallway. And depending on the size of the robot, or if you're, say, an outdoor robot and you're parked in the middle of the street, now everybody has to drive around it in the street. And you may not have the ability to move the robot because it's big enough and heavy enough without it assisting you. So all of these things mean that reliability is super valuable, battery life is super valuable. You can't have a robot that just falls out of the air, say like a drone if it runs out of battery. All of these things are things that mean that we really need to focus on the weight and the cost and the reliability of the computers, which are an enabling factor for providing all of this for robots. So where are we headed next? I'm super enthusiastic about this standardized embedded platforms. I don't know if any of you are familiar with 96 boards. They're developing a standard platform where you can have things like the Dragon Board 410C here that just plug in and have a standard form factor. And in the future, when there's a new one that comes out that'll be either lower power, either lower power consumption, faster CPU, I can just take that and put that into my robot and upgrade my robots in the computer without worrying about reintegrating the entire system, which has been what a lot of people have been doing. You get a custom board, you get everything working, and when you realize you need 50% longer battery life or 50% more CPU, you actually have to go back to the drawing board and redesign the electronics for your robot versus being able to plug stuff in. And also, really big buzzword here is Internet of Things. I would ask you, what are things and why do they need internet? Robots are things. And as I mentioned earlier, robots are not really standalone objects. They're things that are, they're actually a network of distributed. It's a distributed system with lots of robots, potentially components talking to the robots. And some of the things that when I hear people talking about the Internet of Things, they're very focused on the current here and now, which is that you have a little tiny device and it calls home to some server. But really, we need to be able to do things like have local communications. If I have a device in this room and you have a device in this room, they should be able to talk directly. They should be able to be autonomous. There shouldn't be no need to call home to anything else. Like if we're in the same room and we want our devices to interact, they should be able to interact. Similarly, security, there's been a lot of mentions of that. I'll give you an example. We had an intern that came by our office, and he'd finished his internship, he was back for a workshop, but he still had access to the robot, and he wanted to get into the office. So he was outside of the office, he opened his laptop, he logged into the robot, and he drove the robot into the inside of the door that hit the crash bar and opened the door for him to come in. There are major security implications as you start thinking about things that can interact with your world. So he used a $400,000 robot to break in to our office, which had dozens of those. Oh, well, yeah, we would have. He was going back to grad school, so. But yes, he has a job with some of my former coworkers just down the street from us. And yeah, so I was saying everything should be decentralized. There shouldn't be central power or broker that can, say, turn off your device, like the recent Nest just turned off one of their hubs from a company they bought. You had this $300 device, it was working fine. It should continue to work fine whether or not Nest upstream / Google upstream is still supporting you. So, thank you. Yeah.
If you look at some of the robots that you worked on, from the point of view of a power budget, right? How much of the power is devoted to running the electronics versus the actuators for the motors and all that? So where do you get the most bang for the buck in terms of do I improve my power management on the electronics, or I can't do much about motors?
Yeah, so the question is, how do we work the power budget on the robot and sort of balance the power needs for the motors versus the power needs for the computers? And yeah, you're right that there's not a lot we can do about the power needed for the motors. Basically, you can choose to have your robot have less acceleration. If the robot drives slower, it needs less power, if it's smaller. So there's two trade-offs you can make for the motors, which is that you can design the whole robot to be smaller, and we're seeing a lot of that now, where you can design the robot to be smaller so that you carry less weight, which means the motors need to push less hard, which means you can have smaller motors, and then smaller power budget. The challenge we've been running into is that there's a point at which when you make the robot small enough, you can't fit the computer inside it anymore. So the computer is actually one of the limiting factors in. Like you need this space somewhere in the vehicle to fit a computer. And so that's been one of the things as we started looking at home robots. Turns out like a door is about 3 feet wide, and the research robot I showed you, it was designed to be 2 inches narrower than the door. But if you actually try to take that robot into a home environment, it turns out that like you can fit through the door, yes. But the space between your couch and the coffee table is typically like 12 to 18 inches. So if you want to start bringing it into a home environment, you need to start thinking about the robot has to be something like 12 inches wide so that it can fit into places that are human accessible. Now if you're talking about a robot that's 12 inches wide, the computer is suddenly a large fraction of that footprint. You also have to get shorter because if you're 12 inches wide and you're really tall, you're going to tip over. If you have uneven terrain. So you have to start getting shorter, which also decreases your volume. And of course, you still have to fit the batteries in addition. So it's a trade-off onto all these things, but if we can take the computer and reduce the power budget required for the computer, then we can actually fit more in and possibly replace that with battery. So in general, what we do is we pick the form factor for the robot that is required for the application, and then fit as much computation in there as we can to make sure that the battery life meets our needs for the length of the run.
Sorry, did you see any changes in like energy density going from lithium-ion to LiPo or things like that?
Yeah, the energy density in the batteries is important, but that's a major cost trade-off. The lithium ions on the scale of the PR2 running the kilowatt, it had 16 laptop batteries in it to power it, and it would only last about an hour. So.
What are the energy requirements for a robot that wants to do autonomous navigation?
So the question is, what are the memory requirements for a robot that wants to do autonomous navigation? It's very, very dependent on your space and the application, and what sort of things like precision you want to run. So we have our standard way to navigate is we build an occupancy map of the entire space, and we partition that into voxels. And so basically, you can trade off having higher resolution for higher memory usage. So if I want to keep track of this room with a 1 meter grid, that won't take up much space. But that means I can only get within about 2 meters of an obstacle, which would not be adequate for driving through this. To drive through this space with a robot that's a couple feet wide, you need to have at least basically 3 grid cells between you and any obstacle, so you know that there's an occupied one, an unoccupied one, and one that you can enter. And that's the minimum distance you can get. So if you want to start doing that, you start having to cut it down to like probably a 10 centimeter or smaller grid cell. And when you start getting 10 centimeters times the size of this room, and you're going in 3D, so you have to keep track of it gets cubed, suddenly that takes up a lot more memory. Yeah. So the question is, how do we deal with real-time response? And yes, one of my common suggestion is put a microprocessor in that will provide the real-time response. On something like the PR2, we actually had like 3 or 4 different layers of different hardware-based responses. So down to the very microcontroller, they're responding at, I think they were something like 40 kilohertz, closing the loop on the current at the motor. But then the real-time controller was running at 1 kilohertz to send the command to all of those, and then that was backing off to something like 100 to 300 hertz in the Linux-based computer at this core. By delegating and having watchdogs and timeouts, you can guarantee real-time performance, or at least safe fallback behavior. Yeah.
Is ROS configured with RT patches or any other real-time elements of
Yeah, so ROS will run, by default, we run on the standard kernel. A lot of people, if they do want somewhat real-time behavior, they will put RT preamps to make sure that they can give one thread priority. Yeah?
Could you explain the pros and cons of ROS and interdisciplinary, and also how many of the robots that you shown runs on, say, ROS and interdisciplinary?
So, start with the last question. Which of those robots use ROS? The only robots that did not use ROS were the autonomous cars that I showed at the beginning, because those are older than ROS. The video, actually, and there were some of the robots that fell over. 80% of those use ROS. I can't tell you which ones precisely. And obviously, the Unimate at the beginning did not. In terms of pros and cons of what it takes, or pros and cons of ROS, I can give you a whole talk on that. I just say it's an open source platform. There's a large community behind it. If you're interested in robotics, I highly recommend you get involved. Our default is BSD license or Apache 2, which means it's commercial friendly. So, yeah.
From that question, do you see ROS having a lot more traction than like an embedded version of Linux for robots?
So the question is, how does ROS and embedded Linux variants interact? When I say ROS and I'm talking at a computer conference, I need to clarify, ROS is not a computer operating system. ROS is we named it as a robot operating system. It provides the basic features that you need to make a robot move, and it runs on top of a computer OS. So we are actually, in terms of a computer system, we are more of a framework or set of libraries and middleware that runs on top of Linux by default. We actually can compile on OS X, and there are some people that have jumped through horrible hoops to make it work on Windows. But that is not repeatable. They take a snapshot and say, distribute this. Yeah, so if you have a Ubuntu variant on your embedded board, we now have ARM64 and ARM32 binaries, so you can sudo apt-get install based on either Ubuntu or Debian if you just add our PPA. Yeah, if you want more information about ROS, it's ros.org. Yeah?
I have a memory question. Has anybody looked into adaptive grid scaling? So you can identify the size of the object in the room or the size of the room first, and then change the scale of the precision of the sensor based on what it needs for that particular number?
Yeah, so the question is about related to the memory. Has anyone looked at adaptive, changing the grid scale for different applications? And what we actually do, or what we currently do by default, is we only keep track of the high resolution grid cells in the immediate vicinity of the robot. Yeah, so we typically will have a coarser grid map which tries to keep track of the whole building or floor plan that the robot will be navigating through. And then within a couple meters, it will keep track of the high resolution grid, because the high resolution grid is primarily for obstacle avoidance. And so you plan to be able to see it prior to traveling there within as long as you have a couple meters of heads up.
And that happens naturally with the rotating radar system.
Right. We design our sensors to cover the area. There is also knowledge when the robots are navigating about unknown and unsensed areas. For example, if you're driving down a hallway and the hallway turns left, you will not have observed the hallway until you get to the point that you turn to look. So it actually has knowledge about that, and it will not just assume that it's clear and take the close corner. It'll actually try and, we penalize unknown environments so that it will try to actually go a little bit farther and go a little bit slower, but swing it wider to make sure that it doesn't, collide with the person on the other side or realize that the wall did not actually make a 90-degree turn. It only made a 10-degree turn, and there's actually a wall there if you turn the corner. Yeah.
Is there a language of choice for robotics? Do you guys work with them?
So in ROS, we support our primary languages are C++ and Python. The question is, what's the primary language? We like to pick the language based on the application, and the ROS middleware communication layer lets you communicate between different languages. So for heavy lifting, we typically use C++, and for scripting, we use Python. There are bindings for Ruby, Java, Lisp, R, and MATLAB. And there might be other ones that aren't announced. Most of those are community contributed, so. Sorry? No, well, not publicly available. I got an email earlier this week for JavaScript support. The next release will probably have a JavaScript library. So, okay. I think we're basically out of time, so thanks a lot. Anyone else has follow-up questions, come find me up here.